Hello. um, So this is the demo for a collab where you know pytorch basics has been taught. So yeah. So in this basically in the earlier video, as I mentioned, the basics of NumPy and how it is used in deep learning. So NumPy works with a very smaller data. Tensors are used when you are dealing with a large amount of data, and it uses GPU for the computation because the data, the size of the data can be really huge. So tensors handle that. So here we'll learn what tensors are, how to create tensors, what are its attributes against indexing and slicing, and basic operations, mathematical operation, broadcasting in place ops, how to reshape, and the linear algebra, how we can implement in tensors, Einstein summation, and the other things. So this is how we initialize the so for PyTorch we use torch library. So this is how we initialize. So it, as I mentioned, torch uses GPU. So this it just looks for a GPU device if it has. So yeah, if I ran it using CPU, so that's why you can see CPU. But if I just change my runtime to GPU, it will take that GPU, and this CUDA available will be true, and it will later you for the other later operations it will use the GPU. So basically, a tensor is a data container for higher dimension data. So it's a generalization of vector and matrices to potentially higher dimension. So yeah, again, like NumPy, it can be a scalar value. It can be a 1D tensor, 1D, a 2D matrix, 3D tensor, like that, and yeah, more than that as well. So this is how we create. We just do torch.tensor and the value. So this is just a scalar value. That's why you just put the value over here. And again, dot shape gives you the shape, its shape, and endim is for its dimension. So as this is a scalar, it will not have any size because it's just a number and dimension is 0. This is 1D tensor. Here you can see that this is how 1D looks, and the size is 5 and the dimension is 1, and you can also see the number of elements as 5. And this is a 2D matrix. Here you can see the size is 3 cross 3 and the elements are dimensions are 2, because row and column, like that, and the number of elements are 9, total 9. Then this is a 3D vector. Here you can see the whole tensor, and the size is you know uh, 2 cross 2 cross 2, and number of dimensions are 3 because it's a 3D vector, and the number of elements are 8, as you can see here. So why do we use tensors in deep learning is so we will have a lot of the batch of embeddings, word embeddings, tokens. We can show any image data into multidimensional data form, so that can be done using tensors. Batch images can be converted into tensors. So any kind of complex data can be converted into tensors, and then the matrix multiplication and the other linear algebra operations which is used in neural network can be applied to it. So yeah, that is what we do. Then now let's how to create the tensors. First is we can create it from directly from Python list. So we just do torch.tensor and give the list. It will give us the tensor. We can give it a 2 by 2 list, and it will create a 2 by 2 tensor. It can take float values as well and integers. We can also create it from numpy array, just np.array, and give this dimension, the array which we have, and it will create the tensor. Excuse me. Then we have special initialize. Yes. So we can have all zero tensors as well. Just we have to do dot zero and give the dimension. So it will just, it's a 3x4 matrix with all zeros, 2x3 with all ones, and full is whatever value you want to fill in with. You just give it the size and the value you want to get. So it's the whole tensor is filled with 3.14 value. Then I is identity matrix. It's easy to learn that way. So like I mentioned earlier, identity matrix is all the elements in the diagonal are 1, and it is very crucial for linear algebra. And then again, a range is same as the range function in the Python, where you just give start, stop, and end. Stop is exclusive, and then line space is evenly spaced values. Here you can see that. Then random. Yeah, so as we do in a neural network, we randomly initialize the weights, and then we do backpropagation to adjust the weights based on the loss. So here we use this torch.rand function and give the dimension size, and it will create random values. So this is how we initialize the tensors for our neural network use. Okay, this is uniform. So uniform is just 0 to 1. It's good for classification problem. We can also have a normal distribution as well. Normal distribution is basically some values which averages around one value, like any height of a class, it averages around a value. So that is the random integers. Yeah, here we can see the uniform distribution is there's no pattern, everything is uniform, either 0 or 1, like that. Normal distribution, as I mentioned, that it averages around a particular value, which can be 0. So this is how a normal a bell curve looks like, and random integers are like this. Yeah, so there's another option which is creating tensors like other tensors. So if you already have a tensors, you can just use 0 like and reference. You just give the the reference tensor. So let's say you don't know the dimension. Dimension can be dynamic, so you don't know how. You don't want to hard code the values over there. You just do this 0 like the reference tensor, and the reference tensor, whatever the tensor size is, it will create the tensor of the same size. And data type, yes. Then tensor attributes, shape, d-type, and yeah, so this is how you can see the dimension of the data. Dimension batch, rows, column, a number of elements with num_l, number of dimension is ndim, and shape gives you the shape of the tensor. We also have different data types supported, which is float 32, which is default, as I mentioned in the previous video. Float 64, float 16, and this is double small. This is integer 32, boolean. These are supported data types for tensors, and that is what we need. We need numbers in neural networks. So yeah, you won't see any string or values like that. Yeah, you can see it using this d-type attribute. And while creating also, you can set the data type as this, so that the tensor knows that it has to follow this data type throughout. Yeah, that is pretty much it. Then yeah, CPU versus GPU. So pytorch can run on CPU or GPU, but GPU operations are much faster for large tensors. So CPU is good for small tensors and for debugging, but when you are working with a larger data set and working to put it something on production, just use GPUs. And it is essential for neural networks, because as we will see that the size of the the tensors will be really huge, and computing it on CPU will be very slow. So it's very essential that we use GPUs. um, then we have, yeah, we just do device, and if it finds any GPU available, it will just take that value, otherwise it will start using CPU. So yeah, make sure that your runtime is connected to GPU. Then we have indexing and slicing, same as NumPy. Index always starts at 0, and it also has negative indexes from the end. Slicing is same as start, stop, and step, and stop is exclusive, and colon means all elements. So here we can use we can take out the first element like this, second element is a last element, second last element, and 1 to 3 range, first 3 elements, second to end elements, then the every every next element when you want to take. This is for reversing a particular vector. That was indexing, how to use indexing. And yeah, this is same for a 2D matrix, how we can do that. It's 0, 0 is row and column, as I mentioned in the NumPy series, that's row and column. So 0 row 0 column, so this element should come. Here you can see that 0 0 is 1, and 1 and 2 is first row, second element, which is 6. So 6th, -1 and -1, so both last row last column is 9. So yeah, this value came. Then again slicing, same works here. Just go row and column, and you can slice the tensor. Then advanced indexing is yeah, if you want specific elements, you want 0 1, this is row and column. So particular value, you just put these values here, and you can slice the data and get only those particular values, like it wanted 2 6 and 7. So yeah, you can get it using these. Then we also, again, Boolean indexing is also applicable here. You can just put a condition where the value should be greater than 0, and you just pass it to your tensor, and it will give you the elements who are whose condition is true. So only 3 and 5 are greater than 2, so that's why these two are returned. And here we have this condition that it should be greater than -3 but less than 3. So only 1 and -2 is follows this condition, that's why these two are returned. Then again, element wise operations. So here we can do, again, when we do a plus a is this tensor, b is this tensor, when you add it, it will just do element wise addition, subtraction, multiplication, division, power, floor division, and modulo. Excuse me. And yeah, these are the alternative functions. This is add function, sum, mul. So instead of using the operator, you can use these functions as well. They are equivalent. And common mathematical functions, square root, exponents, log base 10, sine, cos, these are also available in tensors. So yeah, tensors are basically created for matrix operations. So yeah, you will find all those operations which can be done on matrices in tensors. Sum, mean, standard deviation, variance, min, max, product of all elements, like that. Then that is, yeah, it's just then here also broadcasting takes is allowed, and broadcasting allows operation between tensors of different type. Your pytorch automatically expands smaller tensors to match larger ones. So yeah, so if we have a this 1D tensor and we want to add it with number 10, we just do this. It will basically create a tensor same of a tensor of 10 with, oops, sorry, I said, with the same dimension as this one, and do the element wise operation and return us the value. Same as this whole vector will get added with the whole, then again with this, and we'll get a 2 by 3 matrix, as you can see here. Yes, so that is also applied. So whatever operations we can do in numpy is as allowed over here. um, so in place operations is, yeah, usually what we do is when we want, let's say we have this tensor and we do broadcast it, add it with 10, we have to store it every time to a new tensors. So what these function, the inbuilt functions add underscore, what it does is it has this in place operations, so you don't have to, it will change this whole the previous t with the new, after adding this 10 it will add it, change the t only, so you don't have to save it every time. So that these are the in place operations, just underscore in the end is there for those operations. So it just helps you, if you forget to reinitialize any variable. Reshaping, again we can flatten images before a fully connected layer, add batch dimensions for single samples, rearrange dimensions for convolutions, and combine and split batch or sequence dimension. So for that we have view and reshape. So yeah, so this is the dimension. It's a single vector, but when we do view 3 to 4, we are just giving 3 cross, make this vector into 3 cross 4 matrix, and it will create a with all the elements it will create the 3 cross 4 matrix. As we saw, it was flattened earlier, now it is in 3 to 4 3 by 3 cross 4 dimensions. Same, we can change it to 3D vector like this. Yeah, that is the, then we have that was to give it a more dimension. Flatten is to collapse dimension, so it's essential for connecting convolutional layers to fully connected layers. So when we have images data, so we wanted to flatten first and then feed it to the model, so at that time we use flatten. So yeah, so earlier you can see the image batch shape is like this, and when we flatten it, it's after flatten its shape is 2 cross 48, sorry. So it flattens, it's no longer a very high dimension data. So now each image is a single vector of 48 features, 3 cross 4 cross 4, like that. Then we have squeeze, unsqueeze, which basically again adds and removes dimensions. Unsqueeze add a dimension of size 1, squeeze removes dimension of size 1. Then we have transpose and permute. It is basically rearranging the dimensions. So transpose is swapping 2 dimensions, so rows into columns into row, and permute is rearrange all dimensions in a random order. So this helps when when you are shuffling the data. You want, when it's going to a second epoch, you want it to be shuffled so that it's not like the neural network is training on the the same data again and again. You just shuffle it and pass it. So yeah, how do we do that? Transpose is dot t. Just use dot t. So this diamond, I'll just show you. This is how the original matrix looks like after transpose. It looks like, it was 2 cross 3, now it will be 3 cross 2. So 1 4 2 5 and 3 6, like that. Permute is, see, the values are shuffled randomly. It's you don't give that, it just randomly shuffles the values. So earlier it was 2 2 4, now it's 3 2 4 2 2 4 2 2 4, like that. Then we have cat and stack. Cat is concatenate all existing dimensions, and stack is add a new dimension. We'll see how that works. Concat is, we have A and B tensors. Concat is just adding the two, combining the two dimensions. So these are the raw one. After combining, how it looks is 1 2 3 4. This 5 6 is appended like that. So this is concat. And these are the three separate tensors, and let's see how stack works. Yeah, so stack is, this was the earlier, these were separate vectors. Stack is just, creating it, adding it in, everything on one. But when you do dimension equals to 0, it's one after another. But when you do dimension equals to 1, it just it does that operation column wise. So 1 4 7 are a one row, 5 8 2 5 8 is 1, 3 6 9 is another, like that. So it gives you more flexibility of how you want to concat your operations, stack your operations. Then linear algebra operations like matrix multiplication, dot product, norm, and matrix decomposition. So matrix multiplication, as I said, it's a heart of deep learning. We have to input, the matrix multiply input vector with the weights vector and then add the bias. So this is how we do it using the @ function, operation. And yeah, the same thing is there. Again, we can use this operation or operator, or we can call this function matmul, which is the same. And again, this has these are just the equivalents for matrix multiplication. Yeah, so it depends on what you want to use. It just explains how it is being done. For inner product, it's dot, or you can use this star is another option to do matrix multiplication. Then yeah, for normalization, we can use the matrix dot norm, this L2 norm. So the torch dot norm uses that. And if you want to do this one uses Euclidean distance, but if you want to use Manhattan, you just point it to p equals to 1. So it will do that. And if you want to do infinity norm, which is max absolute value, you just do p equals to float to infinity. That is there. Yeah, so these are the different methods. Other useful functions are operations are trace. So basically sum of diagonals, determinant. You want to inverse a matrix, just use inverse. And this is the equivalent for inverse. And Then also eigenvalues and eigenvectors. These are mostly advanced ML. So for matrix decomposition, so eigenvalues and eigenvectors can be found using this linear algebra eigen function dot eigen, and just pass your vector. It will give you the eigenvalues and eigenvectors. It is basically used in dimension reduction and matrix appropriation. That is there. Then there's this Einstein summation. The Einstein summation is a powerful compact notation for expressing tensor operations. Expressive name, one can replace many operations using that one particular operation, so you don't have to again put operations chain by chain. And readability, once you know it, it's clearer than chains of operations. Efficiency, pytorch optimizes Einstein sum operations, so yeah, it's good to have. Yeah, so like that we can use this is torch.enum einsum subscripts and just tensor 1 tensor 2. So in the subscripts you can use letters to label dimensions. The same letters, those dimensions are aligned like that. So I will just see an example over here. Yeah, it says so this I comma arrow is like I goes in and nothing comes out like that. Here it is more clearer, but ij goes in and we give j and I, basically swapping, or we can say it as transpose of the matrix. And another can be ij goes in and I comes out, as in yeah, sum over specific axes. So this is ij goes in, j comes out, is keep j and sum over I. Then yeah, it can be done in multidimensional data. These are two tensor Einstein summation operations. So just very when you define it in this way, it just using these two tensors, it applies these operations and gives you the result. So yeah, so it's easier for you to work with instead of again and again writing those functions on your own. So here it is given using a 3D matrix. So this batch and ik goes, batch jk, these two goes, and we get bij. So and this operation we have to do on a and b. So yeah, so it says yeah, it is useful for very complex operations. So here the cheat sheet is given. This means sum all the elements. This is column wise sum, this is row wise sum, this is transpose. I give I is diagonal, then trace dot product is defined like this. Output product element wise operation, multiply matrix multiplication, batch multiplication, matrix vector, attention scores, like that. Then how the activation functions are used, which it's just same as that. So this has a torch has this nn function, nn dot functional, which has all the activation functions inside it. So again, the ReLU, leaky ReLU, sigmoid, tan, GALU, like that are given. The same notation. ReLU says sigmoid is 0 to 1, this is -1 to 1. Leaky allows you some kind of negative values as well, not that much, but then we have GALU as well. Softmax is for multi-class classification, as we discussed in the NumPy introduction. Yes, so same. F dot softmax does the give you the probability of the tensor. So it's basically the whole sum should be equal to 1. uh, yeah, then we come to loss functions again. uh, MSCs, mean square root is for regression data, but if cross entropy is for classification, it is also there. Then normalization, batch norm is there, layer norm is also there. So yeah, it can use that, clipping and dropout. So basically clipping prevents extreme values, so it gives you, makes the value in within a range. So you just clamp your, the function to clip is clamp. You just give your tensor and just, and you give the range in what values it should be there. So yeah, that is what clamp is. Hmm. Dropout is also there. It's randomly zero out elements. This is good for regularization, done for regularization. So this p is 0.5 means 40%, 50% dropout, and the remaining values are scaled up to maintain the expected sum. Then yeah, this is the weight initialization. So yeah, that is pretty much in the tensors introduction. Yeah, thank you.